Good morning. Welcome to class today. I put a question into Mentimeter for you. I asked you what is something you've done, big or small, that you're proud of. So I love it that for some of us it was waking up or that it was coming to class. Those are important. Finishing laundry. In a household with 4 people, that is always my struggle, finishing laundry as well. I love it. Still living, taking that chem exam. Not procrastinating is awesome. That's great. Love it. Oh, for my friend who has nothing, I'm so sorry. You came to class today. That is something to be proud of. Love it. Wow, look at that. Great job on an exam. Tennis champion, awesome. Ooh, yes, voting. Hey, this is a shout out for you all. Election day is tomorrow. Please make sure to vote. Made dinner, was on time. Love it. All right, I will give us 10 more seconds to pop in any other things that we are proud of. All right. We're really excited today. We're all back because the rain's gone, right? I appreciate you all sharing with me some of the things that you're proud of, and I want to remind you that even if how you're doing in our class right now is not something that you're proud of, we still have 2 exams left. We still have lots of quizzes to help us review. You've still got lab stuff. I hope by the end of the semester we are proud of how we did in this class. Whether we get a high grade or not, I hope that we can take pride in the way that we worked on it. So know that I appreciate you sharing with me what you're proud of, and I hope to help you make this something you're proud of too. What we did not get to at the end of our class on Friday was doing some practice with probabilities. Now, I want to remind us, let me go back to what we covered at the end of class to remind you. When we talked about the way that we can make predictions about something happening, remember that there were 2 ways that we could make those predictions. So we talked about how if we have 2 events that we would link with an or, we would do addition for those. So for example, if I asked you, what's the likelihood of having red hair or black hair? If you have red hair, you don't have black hair. So I could add the probability of red hair to the probability of black hair. We would do addition because those things are exclusive. We can only have one or the other. When we start talking about 2 things needing to happen at the same time, when we have an and statement, then we have to multiply things together. So maybe instead of asking you about black hair or red hair, maybe I asked you, what's the probability of having black hair and brown eyes? The way that we would figure that out is taking the probability of having black hair and multiplying that by the probability of having brown eyes. So there's 2 different ways that we figure out probabilities. If it's things that are exclusive of each other, if we use that word and, or, excuse me, if we use the word or, add those chances together. If we use the word and, multiply them. So here's what we're going to do, and I want you to powwow with your neighbors. We are looking at a normal deck of playing cards. So a normal deck of playing cards has 52 cards in it. the first thing I want you to predict for me is the probability of drawing a king or a queen. We use that word or. When I use the word or, is that addition or multiplication? When I use or, that's going to be addition. Okay, so what I need you to do is I need you to figure out how likely are we to draw a king? How many kings are there in the deck? How likely are we to draw a queen? Then we add those two things together. The bottom of my fraction is going to have a 52. There's 52 cards in this deck. Essentially, how many of them are kings or queens? Let's see if we can figure out my probability. How many out of 52? I know that it'll be kind of weird to type me in probabilities, but let's see what we're thinking as we're working on this question. Before I show you the answers, let's work it out together. When I talk about how many kings I have in a typical deck of cards, how many kings are there in a card, or a card deck, excuse me? There's 4 of them, right? There's a king of diamonds, clubs, hearts, or spades. There's 4 kings. So I have a probability of 4 out of 52 are kings. When I talk about queens, it's the same deal. There's 4 queens. 4 out of 52 are queens. So my probability of drawing a king or a queen is going to be 4 plus 4 out of 52. It's going to be 8 out of 52. There we go. Yeah, and so some of us went all the way and did their reducing math. I love it. I promise if you didn't get it down to 2 out of 13, I'm not going to judge you or make you do that. So either correct answers, 8 out of 52 or 2 out of 13 if we reduced it. So there is a reasonable chance of us getting a king or a queen. Now watch this. Now I'm asking you, you're going to draw twice. I want you to draw a king and a queen. When we have the word and, now we have to multiply. So take those numbers we used before, the probability of a king, multiply it by the probability of a queen. Now we're going to get a new probability of drawing both of these cards. My numbers are getting super weird, right? When we multiply my two probabilities, the first one was 4 over 52, and the second one was also 4 over 52. When I multiply those straight across, let's see if we got it typed in for me. Okay, so we all reduced, which is perfect. If you did not reduce, here's the number you'd see over here on the side. So 52 times 52 is 2704. I just did it on my calculator. 16 is 4 times 4. So I had 4 kings multiplied by 4 queens. 4 times 4 is 16, and then I multiply 52 times 52. Notice how this number is smaller than the other numbers that we were looking at. We're less likely to get this exact combination, a king and then a queen. I want us to try one more, just so we're familiar with how to do this. What I want you to try now is we're going to draw a king, and that king needs to be red. What is the probability of drawing a king that is red? There are 2 ways that we can answer this question. The first way we can answer it is by looking at the probability number for a king and the probability number for red. So we've beat to death that a deck of cards has 4 kings. So 4 out of 52, that's my probability for a king. When we talk about the probability for red, red is half the deck. 1 over 26, or excuse me, 1 over 2, or 26 over 52. So we could multiply those numbers together, and that would give us the correct answer. Or if you wanted to do it the fast way, right, we look up at the cards and say, okay, how many are there? So either of those ways will get us to the same answer. Either we have 2 out of 52, there's 2 red kings, or 1 out of 26. Either of those are correct. Here's what I want you guys to take away from this. These kinds of calculations, knowing if I need to add things together or if I need to multiply them, make sure we can figure out which we're supposed to do. If I have the word or, it's one thing or this, I get to add it together. If I have the word and, I have to multiply them together. Keep those rules in mind. Let's do a little spinning here this morning. First lucky winner of the day. Louise? Louise here? Awesome. Okay, Louise, and let's see. My second lucky winner is Alexander. Alexander here? Awesome. So come see me at the end. 2 winners, more to come. All right, let's get to where we are today, which is part 3. If you downloaded the notes for part 3, you saw that we're definitely not going to get through all of that in class today. We're going to finish it up in class on Wednesday. Because we're finishing it on Wednesday, I've bumped your quiz for this module to the next week. So it's not due this Wednesday, it's due the next Wednesday. But here's my caveat with that. We're going to finish this stuff up on Wednesday. I want you by Friday to try to have taken that quiz at least once, because that'll give you an idea of what you need to keep studying before you take it again next Monday or take it again next Wednesday. So even though you have some extra time, please don't forget about this stuff. Please practice with this stuff. And at the very end of part 3, there's a bunch of practice activities for you. So we'll see those on Wednesday. Make sure to check them out. Up to this point, mostly what we've been talking about are things called monohybrid crosses. Monohybrid crosses. This word monohybrid means that there's one trait that I'm looking at. So for example, if I'm looking at peas, which remember are Mendel's favorite thing in the world, if I was just looking at the color of their seed pods, are they green or yellow? That's a monohybrid cross. When we do monohybrid crosses, when we're just looking at one trait of these plants, this helps us to discover something in genetics that's called the law of segregation. I want us to underline, highlight, star this, the law of segregation. What the law of segregation says is that when we're creating gametes for a trait, so for pea pod color, we separate the two alleles that a parent has, and they'll only pass along one. So the idea is we've got two alleles for this trait, but we segregate them from each other. When we segregate them from each other, then we pass one of them along. I can pretty much assure you that this last statement is going to be on the test or on the quiz. So let's make sure we know this. Doing segregation of alleles, so showing the law of segregation, this comes from anaphase 2. Anaphase 2 is part of meiosis. Remember in meiosis that we go through division twice. First we divide just like mitosis, but then we keep going and we do it again. Doing it again splits up the two alleles that each parent has. This is what gives us only one allele being passed on to offspring. So here's what we've said so far. Number one, monohybrid cross, just one trait. We're only watching one. Number two, the law of segregation. I will only pass on one of my two alleles to my offspring. That's monohybrid crosses. But Mendel also did a bunch of dihybrid crosses. And we're going to look at some dihybrid crosses today. When we talk about a dihybrid cross, now we're actually watching two different traits. So for example, if I'm looking at the color of a seed pod, that outside part, and I'm looking at the shape of the seed pod, that would be something I could trace in a dihybrid cross. When we're thinking about a dihybrid cross, where there's two different traits that I'm watching passing from generations to generations, there's two different ways I could pass those traits along. Way number one is what we call dependent assortment. Dependent assortment means that if I have this seed pod color, I'm always going to have this seed pod shape. Dependent, those traits travel together. As we can see on my picture up here, let me get my pointer. When we're traveling together, it's because we're on the same chromosome. So my seed pod color and my seed pod shape, if they're both on the same chromosome, I can only divide them up together. But what we see more often with a lot of the traits that we're tracking is what's called independent assortment. Independent assortment means that whatever traits I'm looking at, so if I'm still looking at Y and R, these things get sorted out in different ways. So they're not on the same chromosome. I can pull them apart from each other. Notice that I could inherit these two chromosomes, giving me YR, or I could inherit this one and this one, or this one and this one, this one and this one. The big idea is I can make more than one or more than two gametes, differences, when we do independent assortment. So independent assortment, what actually happens, if we were doing dependent assortment, where things go together, we'd only have two allele options. And when Mendel crossed things together, this was not what he saw. He didn't see three plants that had the dominant phenotype and just one that was recessive. He actually saw quite a few different offspring. This is because there were 4 different ways that the genetic information could get mixed up and passed along. So notice on my Punnett square over here, if I had dependent assortment, it'd be nice and small. We'd love that one. But actually, we've got independent assortment. Each of the alleles, or the gametes that our offspring could make, or could have, are shown on the two sides. We have 16 different boxes. We see 4 different groups in those boxes. When we do independent assortment, we end up with 9, 3, 3, and 1. What I mean by that is the number of offspring that look certain ways follow the pattern of 9 of them this, 3, 3, and 1. So let's talk about what they look like. 9 of your offspring are going to look dominant for both traits. Now, let's remind ourselves something important. If I'm talking about the dominant allele, do I need 1 copy or 2 copies to see a dominant trait? Ooh, it's been a minute since we talked about this. Remember, dominant means it's the big letter. We looked at that picture, the big letter B, that's cowering over the little letter b. With dominant traits, I only need 1 copy of an allele to show that way. So for 9 of my offspring plants, they're going to show what is dominant because they have at least 1 copy of the dominant allele for the 2 traits. 3 of the offspring will be dominant for the first trait, but recessive for the other, because they got 2 copies of the recessive allele. And vice versa, 3 of them were for allele 2 versus 1. You'll only see 1 individual that expresses the recessive phenotype for both of the traits. The reason there's so few of these is because that would mean I needed recessive alleles all across the board. To be recessive, I could have only gotten those recessive traits. Only 1 of my plants ended up this way. So when we're thinking about dihybrid crosses, these numbers, let's circle them or underline, highlight, star them. These numbers happen 100% of the time. We can make predictions based on this ratio. It's the way that all the pea plants came together to make these different peas. So 9 to 3 to 3 to 1, this shows me what the peas are going to look like. We can look at, again, a couple other traits put together. So now we're looking at the shape of the pea pod and the color of the pea pod. When we do this cross, again, we're going to get some of those same things happening. So we're still going to see that ratio of 9 of them that are green and full, 3 of them that are green with the constricted or the sucked in portion. We've got 1 that is both yellow and constricted. But to get us out of peas, because remember when I asked you what you're going to study, no one said peas. Let's try parakeets. Parakeets, when we talk about those, we can look at traits that tell us both the general color of the wing of a parakeet, as well as whether or not it has these spots. So in parakeets, we've got 9 of the offspring that have the yellow wings and the black spots. We've got 3 of the offspring with the yellow wings, but no spots. Then we've got 3 of the offspring that have spots, but not yellow, and only 1 that's down here with no spots and white color. So if you're given a Punnett square like this, or if you're given a number, if I tell you, hey, I only got 1 parakeet that doesn't have spots and it has white wings, you can tell me, oh, those must be the recessive traits. Or if I told you I got 9 that had yellow wings and black spots, if I've got that many, that means it's the dominant trait. So know those numbers, know how we could use them to figure out the genotype of our offspring. When we do a dihybrid cross, like we saw in our pictures with the pea plants or the parakeets, things get a little bit crazy. So we're looking at two parents here. These parents are heterozygous for two traits, Y and P. Because they're heterozygous, they can each make 4 different allele combinations. They can each have 4 different combinations of their genetic information, which means when I build my Punnett square to figure out how they cross their information together, we get this massive thing. This massive thing is a 16 square Punnett square, where we'd have to go through and put each of these different gametes along the top, and each of them along the side, and when I cross them together, I end up with all the different offspring. You could calculate the frequency of a particular combination by writing everything out on the table, but what's a lot easier to do if we're talking about 2 different traits is to do multiplication, to do that rule that we started with. We're doing the AND rule. So I need to have this trait and this trait. To figure out how likely that is to happen, I can look at each of the traits individually. So let's say that we've got offspring that we want to find lowercase r's and one big and one little y. This is our goal. We want to get to here. Our parents are right here. So I could individually make little Punnett squares just for gene R, because this is much easier. Make a Punnett square just for gene Y, the kinds of offspring I could make. Now that I've made those Punnett squares, now I'm going to go back to my offspring and see what I want. So I'm looking for an offspring that has 2 little r's. So I go over to my table here. Nope, 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 yes. My probability of getting 2 little r's is 1 out of 4. So 2 little r's, 1 out of 4 of my offspring will have that. Now I'm going to look at my y's. For YY, I want uppercase and lowercase. I want heterozygous. I come over here on my Punnett square. Nope, yes, yes, nope. 2 out of 4 of my offspring are going to get this genotype, heterozygous. So I've got homozygous recessive 1/4 of the time. I've got heterozygous half the time. When I multiply them together, let me do my best to write on my slide here. So half the time, oh, no, excuse me, 1/4 of the time we're getting RR. I multiply that by half the time I'm getting heterozygous. I end up with 1 out of 8 of my offspring are going to have this exact genotype. We could have gone through and made a 16 square Punnett square. We could have done that, but it's a lot easier to do these 2 little 4 ones. And then we get to use that multiplication rule like we did before. If I need this allele and this allele, we multiply together. So let's take a moment and practice doing this. And Dr. Allis realized, perhaps you've seen, my Punnett square is a little too big on the 16 one. I gave you a 5 by 5, so the good news is it's not quite that big. I want you to figure out the probability of making this offspring and this offspring. There's 2 ways to do this. Way number 1 is to fill in my huge square over here and count. But way number 2 is to do my 2 little Punnett squares. So let's look up here. Here is the genotype of my 2 parents. So my Punnett square on the left, I'm going to say that's my Punnett square for trait W. So if I'm parent number 1, I've got a big W and I've got a little w. And my up and down, my vertical is going to be that F, or excuse me, we're still in W, big W, little w. That's parent 1 and parent 2. I'm going to leave you to fill in that Punnett square. We're going to go down to the other one, though, for trait F. Parent 1 has big F and little f. Parent 2 has big F and little f. So step 1, let's figure out the likelihood of getting this combination of W's and multiply that by this combination of F's. That's my first one. This combination of W's, this combination of F's. We'll multiply those together to figure out the probabilities for each of these things. I saw a question, possibly? No? Okay. So let me pause and give you a moment. Please chat with your neighbors as needed. We're going to fill in these two little Punnett squares so that we can multiply our probabilities together. Yes? I apologize. Say it a little bit louder. These are my parents. My parents are what's going, are giving alleles to the offspring. So when I'm looking at this one up here, I'm looking at the offspring, what's made from the Punnett square. So the letters, the size of them that I put on there come from the parents. And what I get out of it, these guys that we're focusing on, these guys are going to be on the table. Yeah. Thumbs up if we've figured out the probability for both offspring. How many of us are there? Okay, about half of us. I'm going to give us about 30 more seconds. Keep working. If you've figured out the probabilities, I'll pop this question in for you to work on while we wait. So I'll show you the reason why it's better to do the little Punnett squares. I went through and I just filled in the first line of the big Punnett square. That took me a lot of time because each of my parents have 4 different possibilities for what alleles they're passing along. And I have to pair those each with 4 different possibilities from the other parent. And I better hope that I don't make a mistake, and then I got to go through and count them. If we just do it with the little Punnett squares, it's going to go a lot faster, and we're going to be a lot more likely to get the right numbers. So when we're looking at our possibilities here. So the first offspring I want is WWFF homozygous dominant across the board. So I have two traits. I've got an and situation here. I'm going to multiply. So you all filled in the table. I did not, which means I need your help. What was my probability of getting big W, big W? What was the probability of that one? How many on your table over here, when we crossed it, how many of them were two dominant alleles? How many do you see there? Yeah, just one, right? Here, let's do our table together. Two big W's in this position. We've got a big W from the left and a little w from the top. Then we've got a big W from the top, little w, and two little w's over here. So first step to predicting this gamete, or this offspring population, is I look for my percentage of WW. That's 1 out of 4. 1 out of 4 of my offspring have that genotype. Now I'm going to multiply, because it's an and. I'm going to do my F Punnett square as well. So big F from both of them. Big F from the left, little f from the top. Big F from the top, little f from the left, and two little f's. Based on this little Punnett square that I made, I only have one offspring out of 4 that have the two big F's. When we do our multiplication, we get 1 over 16. So if I filled in this whole table with all those traits, only one of the offspring that I made would have that genotype. Two big W's, two big F's, 1 out of 16 chance. Now let's go over to big W, and little f, little f. I have like no space here, right? But let's start with this first allele. Big W, little w. When we look over at our Punnett square over here, how many of these gametes have big W, little w? Not a trick question. 2 of them, right? Number 1, number 2. So 2 out of 4, or if you want to reduce it, you can make it 1 out of 2. I don't care. 2 out of 4 are heterozygous. Now I'm going to go to my F gene allele. My number of gametes that have 2 little f's, only one of those, 1 of 4. So now I do my multiplication, and I end up with 2 over 16. Which means if I filled in that entire table, and I did it correctly, only 2 of them would look like that. We need to practice with doing these kinds of crosses. Because on the quiz and on the exam, I will ask you, what's the probability? Probability, by the way, is the same as, you might see the word, the likelihood, or how many offspring look like this. They're all the same kind of words. How many, what's the likelihood, what's the probability? Break it down, 2 little Punnett squares, and multiply those numbers together. So I tossed up a question, and I want to go back to it to give us a quick mental break, because we've been doing a lot of math. I know math's not our favorite. If you have not already, shoot me a quick text. How is dependent assortment different from independent assortment? Might have to go back a couple of slides. Dependent assortment and independent assortment. If you're still typing, please keep typing. It'll update for me. Let's see where we're at right now. There's lots of different options we could put here. I like it. Okay, so our biggest things on there is that dependent assortment means that my alleles go together. They're stuck together. That makes my Punnett square a lot smaller. We like that because it's not as big. But most of the things we're talking about have independent assortment, which means, like we have on here, independent assortment, they're separating from each other. So the big difference between those two is whether or not we divide up the alleles for the different genes. That's absolutely right. Let me see, we did that one together. All right, let's spin the wheel. We could do some math on this. I won't make you do this. What's your likelihood of winning? And then what's the likelihood of you and your neighbor? I won't make you do that. Dorian here? Awesome, Dorian's here. And one more. And Lisa wins again. Oh my gosh, Lisa. You've won a lot. Hey, in a couple of classes, I'm going to make a wheel for all my friends who have not won the entire semester, and I'll spin that wheel sometimes too. So I try to help out my friends who haven't won. The last thing I want to talk with you a little bit about is moving away from the pea plants. We're going to talk a little bit about how we do this in humans. So when we're talking about humans, inside each of your cells, you have 23 pairs of chromosomes. So one chromosome from each of those pairs came from mom. One chromosome from each pair came from dad. Half of the genetic information came from those places. Those chromosomes are divided into two different groups. So the first group is called autosomes. 22 of our pairs are autosomes. And once you've written that number, I want you to underline the word autosomes. Autosomes. It just means a chromosome that has all of the normal genes on it. It's not what we call a sex chromosome. So there's one pair of sex chromosomes that determines your sex, 22 pairs of autosomes that determine everything else. When we talk about the sex chromosomes, there's only two possibilities. Either you have two X chromosomes or an X and a Y. This is our normal sex chromosome arrangements. So when we're talking about all these different traits that we're doing things with, most of them are going to be on these autosomes, the majority of your chromosomes. In humans, we cannot ethically do all these different crosses, right? That would be very sketchy. So what we can do in humans, though, is look at the way that different traits have been passed on from generation to generation. So we have these things, like you see here, called a pedigree. And a pedigree is, I'm looking at everyone in your family. I am representing them here on this chart to help me get some ideas about what's going on genetically in your family. So when we look at the phenotypes of everyone, I can start to make some predictions about genotypes. And I'll tell you what I mean by this, or I'll show you how to do this here in a moment. If I can see who ends up being dominant versus recessive, I can sometimes get that off of these pedigrees. When you look at a pedigree, the first thing we need to make sure we know is males and females are represented differently. Males are represented as squares, females are represented as circles. And when we look at the arrangement of these different people, males and females, the level that they're at is an indication of a generation. So here's my parent generation. My parent generation has these offspring. One of their children, one of their daughters, has these offspring. Each level is a different generation. And when we look at the horizontal lines that are directly between people on a pedigree, that indicates mating. So that indicates where offspring would come from. So original parents generated these three offspring. This husband married this daughter here, and they generated offspring as well. So different generations that we see along there. We can also see mating relationships and those kinds of things. When we look at a pedigree, it's going to look different when we're looking at a disease that is dominant versus recessive. So what I want you to first underline, highlight, star on this picture up here is the word dominant. When I'm looking at a condition that is spread in a dominant pattern, what that means is you only need one copy of the gene to express that condition. So here's my family, father and mother. Father has a mutation. He has one copy of this disease allele. But he also has one normal copy. He only needs one copy to express the disease. When we look at the offspring of these parents, two of the offspring are affected by this disorder. Two of them got his mutated chromosome. But notice that two of them also didn't. Two of them got the normal chromosome, if you will. So when we look at an autosomal dominant disorder, you'll have some offspring that are affected and some that are not. An affected parent will always have some that are and are not affected. If we want to put this back into the circles and squares, I've built for you what that looks like. Affected individuals will always be shown in the darker color, so we're seeing the dark black. So dad, this dark black box, is affected. Mom is not. We've got two unaffected children, boy and a girl, and then an affected boy and an affected girl. This is what it would look like if we had, and let's underline, a recessive disorder. Recessive disorder. When we talk about a recessive disorder, you'll see two parents who are unaffected. Neither of them show this disease, but we see children who are affected. When you have a recessive disease, you need two copies of the directions for that disease. So the way you know we're looking at a recessive disorder is parents aren't affected, some of the offspring are. So again, to turn that pedigree into our boxes and circles, mom and dad both do not have this disorder, but one of their children does. That means that mom and dad both must have a copy of the allele that would lead to this disease. So, affected parent, affected offspring, probably going to be a dominant. Unaffected parents, affected offspring, that's recessive. When we look at those two pedigrees, here's the last thing we're going to land on. We're tracking what we see in the picture here. I've got two parents that are both affected by a condition. When they have an offspring that doesn't have that condition, that's going to tell me that this has to be a dominant disorder. Because if I have offspring that aren't affected and parents that are, that means that the parents are heterozygous. So the parents, like it says here, have an affected gene and an unaffected gene. Some of their children aren't affected. But remember with this one, when a child has the disorder and the parents don't, that means we're looking at a recessive disorder because the parents don't have it and the child does. We will pick up on Wednesday talking a little bit more about